My name is Mika Rautio. I'm coming from Nexi Group. Nexi Group is a large European paytech company operating in over 25 countries. We are offering services for issuers, acquirers, and merchants. In Nexi Group, I'm working as a senior security architect. What that means is that I'm trying to protect our card acceptance systems and ensure that they are compliant and secure. On my free time, I'm playing a bass guitar on a punk band, so if this talk is a bit out of tune or offbeat, it's just me, so don't worry. So I'm first going to talk about the project where we migrated an e-commerce system from one to another. And then I'm going to focus on how did we actually do the cardholder data migration and how did we protect the data during the migration. So this project is very common to large entities. You might have had mergers and acquisitions. You seem to realize that you are having a lot of services. A couple of services are doing exactly the same thing. We noticed that we had two e-commerce systems that are doing exactly the same thing. And we decided to sunset one and replace it with another one. Problem with this kind of migration is that we had explicit high availability requirements. We had to have zero planned and unplanned downtime in the project. And both systems were very active at the time, processing millions of cardholders and cards and transactions. Here you can see our production go live last leg. So we had two cardholder data migrations, one initial load where we moved all cardholder data to the new system, and then later on we had so-called delta migration where we sent updates to that cardholder data to the new system. We had production testing and internal piloting to ensure that the use cases are supported by the new system. Because in the end, when you're comparing two e-commerce payment service platforms, those look on a high level very, very similar. But then the devil is always in the detail, and we had to test all the use cases out. And lastly, we had to do the actual go live, which we did on a gradual fashion. We implemented a dynamic transaction routing proxy that sit on top of both systems, and then it decided which system, the old one or new one, will get the transactions. And we were able to gradually move the user loads and cardholders and transactions to the new system with this approach. And we managed to do it without users noticing anything changed. But let's now jump in and talk a bit about the cardholder data migration process, which is the main part of this talk. So in a nutshell, you have point A, a database, and point B, the destination database, and you need to move the data somehow. And how the movement can be done depends on what kind of data you are moving. We are talking now about PCI data, so we need to, of course, abide with the rules and regulations what comes to PCI and GDPR and whatnot. How we decided to do the cardholder data migration was by implementing a microservice using AWS Lambda. The purpose of this microservice was to export the data, so basically download the data from the source database and then transform it to the format that the new service is expecting. And also validate the data, generate statistics and errors and anomalies into the logs, and then output the format. And this process was triggered by an administrator of the source environment. Then, of course, when the Lambda or the microservice had done its job, the administrator had to verify the results by looking at the logs. Do the statistics look good? Is everything as we expect? And then also look at the end product. What does the data look in the AWS S3 bucket? Is it proper? And after that, the administrator uploads the data to the new system, where it's imported and verified. And last but not least, the whole export infrastructure is being deleted because we don't no longer need it after the migration. We just retain the logs just in case. And this is the high-level picture how we move the data. But this doesn't still answer to the question that how did we protect the data exactly. And let's go into that detail. So, of course, when you're doing PCI DSS, you're having a lot of requirements, a lot of controls. You're needing to check that PCI DSS AOCs are properly done. You need to check the due diligence. You need to check the scopes and everything. What we are now talking about are the controls that we felt were the primary controls to secure the data during the migration, so very technical controls. First, data minimization and short data retentions. So we want to minimize the data that we are moving. So we first assess that what is the absolute minimum needed by the destination system, and then we actually went with the absolute minimum. No need to send more than what you need, actually. And also, during the data migration, we had to temporarily store data, so we implemented automated data retention controls. So the data during migration was automatically deleted after a very short while of mere hours or minutes. Then we had zero trust and least privilege type of controls here. So each endpoint during the data migration had their own authentications, authorizations. We had strict network access controls in place to prevent the data from accidentally leaking while being processed. The exporter microservice itself had only access to the source database and to the export S3 bucket that we named and logs. So it didn't have any access to internet, it didn't have any access to public DNS or anything to exfiltrate the data. It couldn't have sent Twitter tweets even if it would have wanted. But what we think is the most crucial technical security control is the strong encryption and end-to-end encryption. We used in-transit and at-rest cryptographic controls. So in-transit meaning when the data moves from one endpoint to another, and at rest when we are storing the data temporarily somewhere. For in-transit, inside the source environment, we used TLS 1.2 to protect the data. And when it was moved to the destination, we used SSH2 primarily. For at rest, we protected the data in the AWS S3 bucket using AWS KMS, Key Management Service. And we also implemented, using OpenPGP, encryption of the whole migration payload. So the payload was actually encrypted by the exporter microservice using the new service provider entities, cryptographic keys, and it was then only decrypted in the end when it arrived to the new e-commerce service provider. This means that we didn't have access to the data ourselves even. And this was the intention. You might ask that why do we have so many cryptographic encryption controls in place? I'm thinking this as the so-called belt and suspenders mechanism, or maybe couple of belts and couple of suspenders. technically speaking, if you're having, let's say, AES encryption, advanced encryption standard encryption, it does not make sense to encrypt a file twice. It doesn't add much value or confidentiality or integrity to the details. But in this case, we found value by encrypting data a couple of times because we had different entities and different key management procedures. This means that even if one entity's key management practices would have failed during the migration, we would still have had confidentiality and integrity with the data. And we are talking about large amount of data, so we want to keep our customers safe and secure. But these are the protocols. Behind the protocols, there are the encryption algorithms that need to be carefully selected and designed if you want to have certain properties to protect your systems. We had a lot of encryption algorithms in play due to having a lot of different protocols in play. And we had key exchange algorithms, authentication algorithms, data encryption algorithms, and integrity and authenticity related algorithms. And we carefully checked that the properties are right in order to ensure that the data is being confidential and that the data integrity is being kept. For instance, in transit encryption, we used ephemeral curve Diffie-Hellman algorithms to ensure that we have perfect forward secrecy when we are transferring the data from one endpoint to another. Reason for this is that basically perfect forward secrecy means that you are having session keys, data encryption keys that are unique per data transfer session. And when we are having unique keys, it means that even if later on in the future our endpoints that we used for migration would get compromised or we would get data breaches for those, we could still be confident that the data we transferred back then would be secure due to this protocol. Then we had for authentication and data encryption, we used 128-bit security strength for keys and algorithms. You may ask why, and the reason is that, well, NIST recommends that you should have 128-bit security strength if you want to protect data until 2030 and maybe a bit beyond. Also, European counterparts like BSI are recommending to have a higher encryption, effective encryption strengths than 112 bits nowadays. So that's the reason why we did it. But then the question is that how secure is 128 bits? Well, it's like if you want to like brute force and pry open the encrypted data, it basically means that it's like you need to find the encryption keys and it's like finding a needle in a haystack. Well, that's actually a bit bad comparison because it's more or less finding a water molecule in a lake. So it's that many keys you need to brute force in order to decrypt data. And of course, we also had integrity protections. We don't want the users or their cardholder data to be, let's say, your PAN number is off by 1. That would be horrible. Or at least it might be good for me if somebody else pays my bills, but I mean that users don't want to see that. So that's why we used strong integrity controls like with SHA 256 to protect the integrity so that the payloads are bit by bit the same that we expect them to be. And this is how we protected our data. To close this, the question is that why am I even talking about protecting of data being migrated? Well, I think that issue with security is that we are living in the world of assumptions. It's assumption that RSA encryption algorithm is secure, and the assumption is based that we expect that you cannot factor large prime numbers easily. And that's how cryptographic controls work. And also security controls are based on assumptions. We are assuming that they are good enough to cover the risks and threats we are facing. And I'm hoping that we together in the industry would also share our experiences and ways we are doing these cryptographic controls or security controls for our systems. PCI standards and PCI DSS are providing good baseline and yardstick how you need to do your controls. But in the end, you need to decide what is your risk or threat level. We believe that cardholder data should not be seen by humans in plain text form ever. And this is why we did this kind of data migration controls, because no humans were able to see the data. It was only the source application and destination application that saw the data, plain text, and everywhere else it was encrypted. So, when you're doing data migrations, scope your migration, understand the data you're having, because that is affecting the regulatory and standard frameworks you need to use. Understand the lifetime of your data. So when you're protecting some data, it's good to understand that do you need to protect it for 1 month, 2 years, 20 years. If you're storing a military secret, it might be that you need to keep it confidential for 50 years. For cardholder data, it might be less, it might be more, who knows. So when you understand the lifetime of your data, you can better decide the algorithms and controls that you need to keep the data confidential. And lastly, if you haven't yet started, please start considering moving towards higher effective key strengths and algorithm strengths. We are still having a lot of entities that are using triple DES or RSA 2048 bits. Those are still valid depending on scenarios, but you should start considering how can you start moving and migrating towards AES, or how about taking care of the post-quantum threats? How can you incorporate the new NIST standards that are intended to mitigate some of the post-quantum computer-related threats for confidentiality of the data? Anyway, also the assumptions are really interesting, because back in the stage, the organizer said to me that you don't press the red button, but I'm really keen to try to press it at the moment, but maybe I'll let the organizers tell me what it does later. Thank you very much.